Hello, everyone, and welcome to today's seminar of our seminar series on non-Hermitian physics. Today, we are very excited to have Professor Dr. Ewold Verhagen with us here today, who will talk about optomechanical metamatter. But before we get started, we would like to remind you of our house rules. So please keep your camera and microphone switched off during the talk to save bandwidth. You can ask questions by either typing them in the chat or by raising your hand. However, we will essentially only take questions after the talk. If you're joining us from YouTube, please write your questions in the chat and we will forward them to the speaker. Before we get started with the seminar, a quick announcement. So next week, we will have a talk by José Lado from Aalto University on static and dynamic topological modes in interacting non-Hermitian systems with tensor networks. So now let's get started with our seminar of today. We are very excited to have Ewold Verhagen here from EMOF Amsterdam. Ewold leads the Photonic Forces Group at the Center for Nanophotonics at EMOF and is also a part-time professor of applied physics at the Eindhoven University of Technology. And he focuses on nano-optomechanical systems in his work. He also did his PhD at EMOF on plasmonics in metamaterials, and metamaterials is still an important theme in his work, as you can see from the title. Then he joined Tobias Kippenberg's group at the EPFL, working on quantum optomechanics. And the interaction of photons and phonon is still a central theme in his work, as we will now see in his talk. And now he's, since 2012, he is the group leader of the Photonics Forces Group at EMOF. So we are very much looking forward to your talk, Ewold. Stage is yours.
Thank you so much. Let me share my screen. All right, I think you should be able to see it now. Yeah, thanks, Clara, for introducing me and also for inviting me, of course, to this exciting seminar series. I'm happy to speak a little bit about the work that we do in my lab. I understand that the last two presentations were more theory centered. I'm going to show you some experiments on how we induce and control non-Hermitian dynamics in actually optomechanical systems, and I'll show you what we do, how we do it, and what kind of physics one can explore. Importantly, this is a collaboration with a few people, including actually the chair of today, Clara. She did not instruct me. I will full disclosure on what to speak about, but so I will take the prerogative to actually speak about some work that we did together with her, also with other theory collaborators. Javier Del Pino was in my group before, now at ETH. And Matteo Brunelli, now at Basel, and Andreas Neunenkamp, who is in Vienna. And so, importantly, the experiments that I will show, they have all been done by Jesse Slim, who has since moved to Queensland. So, the title of my talk is Optomechanical Metamatter. I'll tell you what I mean with that and what I don't mean with it. We will look at various effects that are related to the breaking of symmetries in transport phenomena like non-reciprocity, to some non-Hermitian dynamical behavior, and in particular non-Hermitian topological phases of matter, which is some recent and unpublished work that I will be talking about, and which is very much a collaboration between this team. And so when we talk about topological phases, these have, of course, been gaining a lot of interest in recent years. People are, of course, very much excited by the interesting phenomena that they induce, in particular, how in topological insulators, for example, one can have this global description of the states of a system, of a material defined on the band structure of such a material, guarantees some interesting properties. Specifically, the bulk boundary correspondence in a topological insulator tells us that there's these topologically protected edge states that must live at the boundaries of a system that are topologically protected by this the description of the global description of the bulk. And this is a very useful feature that has led to many interesting phenomena and proposals. And there's various different kinds of topological insulators. You probably have heard of these in fermionic systems. There's, for example, the quantum Hall insulator, which is a two-dimensional electron gas in a magnetic field, where the magnetic field induces insulating behavior in the bulk, but this is connected to the existence of conducting states at the edge that have this unidirectional, so chiral nature, showing the broken time reversal symmetry that's related to the biasing magnetic field in this system. And these are topologically protected states in a way that are responsible for the quantized Hall conductance. And there's the related quantum spin Hall effect that relies on spin-orbit coupling. And also in other dimensions, one of the simplest topological models is the SSH model that describes electrons in polyacetylene molecules, including the edge states that can form at the ends of this chain that are related to the specific crystal structure of this system, and also Majorana zero modes that can exist in superconducting nanowires, for example, and that have attracted a lot of attention also in the context of using their topologically protected nature to perform some interesting quantum computing applications. Now, these are all fermionic systems. In bosons, there have been in the last 10 years, or a little bit more maybe even, a big push to see similar kind of phenomena in all kinds of domains, emulating, for example, these kind of effects in microwaves, in photonic resonator arrays here. This is a macroscopic mechanical system and also an on-chip micromechanical system that through different kinds of mechanisms display topological phases of electromagnetic or sound waves. And especially in this context of bosonics, there is the interesting direction of combining topological phases with non-Hermitian behavior. Of course, loss and gain and the control thereof comes very natural in bosonic systems. And so non-Hermitian topological phases gain a lot of interest. On the one hand, one can simply wonder, okay, what happens to a topological state if you add loss and gain in a specific way, and can then, for example, these edge states then lead to specific and topologically protected lasing states, for example, like in these kind of experiments. But there's been a big push also to understand actually topology in non-Hermitian systems. This is a small subset, I would say, of works in this area. A lot of theory works, also some experiments that ask the question, okay, what kind of topological invariants can one have that maybe are not present in Hermitian systems that are related to the non-Hermitian behavior? So loss and gain and suitable distributions thereof. And what are then the properties of such systems? How can we describe their topology? How can we understand things like the bulk boundary correspondence? And are there specific applications of such phases of matter if they exist? And specifically interesting could be the use of such systems for sensing applications, and as to provide specific topological protection of amplifying functions, for example, in particular in the quantum domain that people have thought about. Okay, and so this forms like the backdrop of my talk, I would say, and I'm going to actually talk mainly. I'm going to steer towards a specific type of non-Hermitian topological system, which is basically the bosonic analog of a Kitaev-Majorana chain, as it is known. I'll tell you this later on why this is an interesting system to study. And this has been put forward first by the group of Ash Clerk a few years ago, and there's a number of other works, for example, from the group of Lorenzo Piola, who have studied this system also. And it is really the analog of a Kitaev chain, which is the canonical one-dimensional model for that predicts the existence of Majorana zero modes in a superconducting one-dimensional nanowire, basically. So what this model consists of is a chain of resonators, atoms, if you will, that are interacting both via a regular hopping link, but also via a pairing interaction that is related to the superconducting pairing behavior in a fermionic system. And if we simply write this the Hamiltonian of the system in terms of the ladder operators, these are now the bosonic operators. So then we recognize a hopping term that annihilates an excitation on one side and creates it on the other, on the adjacent one, and a two-mode squeezing interaction, which is the pairing interaction, if you will. And so now this bosonic system emulating the well-known fermionic Majorana system actually has a lot of interesting features. Many of them are not, as you will see, directly analogs of the things that Majoranas are famous for, and the applications in quantum computing, because they don't obey, of course, bosons don't obey fermionic statistics. But there are some other interesting features that have, in part, been predicted by Ashclerk in this group, and we will be exploring them in the talk. So, in fact, this two-mode squeezing interaction, this is what induces non-Hermitian dynamics in the systems. It annihilates or creates particles in these sites in pairs, if you will. It doesn't conserve particle number, this coupling, and it's classically speaking, this is just a form of parametric driving of the system. So single mode squeezing is the same as parametric amplification, and two mode squeezing, which is what we say is a variety of thereof. So and that induces non-Hermitian dynamics is actually very obvious, and because if you have parametric amplification, that is a change of or modulation of the frequency of a single resonator at 2 times its resonance frequency. This is what a child on a swing does to amplify their motion. They extend their legs and, in order to amplify motion that's in phase with that parametric drive, and at the same time you damp the motion that's out of phase. And this gives rise to this is why it's called squeezing, because if you start with like a Gaussian state, then the motion of one quadrature, so one particular phase controlled by the drive, is amplified. The other one is damped, and that is also associated with basically complex eigenvalues that describe the dynamics. One that is corresponding to the amplified quadrature, and the other one corresponding to the damped one, and so. Yeah, this amplification and damping shows you that the non-Hermitian character, even though, of course, the Hamiltonian itself is a Hermitian thing, the dynamics that it ensues is non-Hermitian. And so we can use this, as you'll see, to our benefit to construct different systems. But I will show you how we do this, and for this I want to introduce, because maybe not all of you are familiar, a little bit the context of cavity optomechanics. Because what we will do is that we will make these sites in this chain be mechanical resonators, and we use laser fields in order to couple them in the right way and to establish such a model. And as I will show, this allows many more things than just this bosonic Kitaev chain, and we will see some of them along the way. But so in cavity optomechanics, this is you can create the coupling between a mechanical resonator and an optical mode, which is itself established because the motion of the mechanical mode is changing the frequency of the optical resonator. And so you can use that to very sensitively read out the motion of the mechanical resonator using a laser that's reflected from this optical cavity. better the optical cavity is, the more sensitive you are, and the smaller it is, the larger this frequency shift. So also the more sensitive you are. And at the same time, the photons in this cavity exert a force on the mechanical system. This scales with the same parameter, the frequency shift per unit displacement, and it's controlled by the number of photons in the cavity, of course. And so this kind of dual interaction happens in many systems where you have an optical cavity that is somehow deformable and coupled to a mechanical degree of freedom. You see many different examples here that look very different, but they're actually all described by the very same physics, from superconducting drum resonators to these optical ring resonators, photonic crystals, membranes in cavities, even trapped particles in cavities. Now, if you have that kind of an interaction, you can actually study some interesting dynamical behavior in systems that are multimode, where you have multiple optical and mechanical resonators that you control in using these laser fields. Basically, you can say that the time-varying optical forces in such a system basically create a time-modulated potential for mechanical motion that we can tailor at will, and which we do in this in our work. And the first ideas in this kind of direction within the context of optomechanics were put forward about a decade ago or so. This is one of the early works that recognized that if you have a system where you have multiple mechanical degrees of freedom, here labeled as B1, B2, B3 here, and they're coupled via this parametric coupling to an optical field, it's A1 and A2 here, then you can induce some interesting behavior, because basically a laser that's driving this system can induce transitions, so a coupling from that transfers an excitation in a mechanical resonator to an optical field, basically in a Raman-like process, scattering a photon to a higher frequency, taking up a phonon, and this corresponds to a hopping interaction between these degrees of freedom, and the laser field that controls the rate at which this coupling occurs, and also the phase at which this coupling occurs. And why people were interested in this is that they realized that, yeah, you can then create, for example, loops of resonators where excitations can go around a circle, and that since you can control the phases of the transfer of excitations in such a system using the phases of laser drives, you can break time reversal symmetry in such a system and make the excitations, for example, mimic those of electrons in a magnetic field that breaks time reversal symmetry. If you have a loop in which electrons can flow that encloses a certain flux, this flux can correspond to a phase of electrons flowing around this loop, or a phase difference between two different paths that is proportional to the flux. The phase along such a path is proportional to the magnetic vector potential. And this depends on the direction of the magnetic field, and you can use this to induce some interesting behavior. The Aharonov-Bohm effect, for example, or you can create use this kind of broken time reversal symmetry to block transport in one direction through interference, or create a circulating behavior. And in fact, in optomechanical context, this was pursued a few years ago in various types of systems, and we wrote a review article about this a few years ago to make photonic isolators and circulators. Now, you can, although, think bigger, quite literally, if you have larger arrays of resonators in which you can control these phases and induce effective magnetic fields, then you can create, for example, the quantum Hall effect in a lattice of resonators, because this is basically exactly what the Hofstadter model for the quantum Hall effect does. If you have a total loop phase on each plaquette here, this mimics a magnetic field, and it can induce these effective edge states that are topological states, like in the quantum Hall effect, and they are unidirectional. They go only in one direction that's given by the magnetic field. Crucial here is, the fact that through these optomechanical interactions we can convert the frequency that between the different sites here. and that allows you to induce these kind of non-trivial loop phases and emulate a magnetic field, even though there's no real magnetic field present. Now, and this led this idea led the group of Florian Margaard and his co-workers to imagine, okay, if we have optomechanical systems where, for example, in this photonic crystal implementation, you have optical and mechanical degrees of freedom coupled locally, and we drive them through laser drives, you can basically create lattices in which you mimic the quantum Hall effect and induce topological states of both light and sound, basically the optomechanical polaritons going on. And it was an inspiring idea for us. There was a big challenge though, which is that for this to work properly, you actually need the mechanical frequency to exceed the optical line widths of all of the cavities. And at the same time, all of the cavities need to be tuned to the same frequency to allow not having a gazillion lasers controlling this system. And so this sets an extremely high bar for the experimental control of the system. So this hasn't been exactly realized, but we thought of a different way to basically create similar type physics, and I will in relatively small lattices, I would say, and I will introduce the system now in which we do that. And so it is this system, we call this a sliced photonic crystal nanobeam. It's made of silicon. It's freestanding. It's sitting on a chip supported at both ends, and you basically see two beams here, about 20 micrometers length, and they can vibrate. And so in different ways, these are just the different natural modes of these strings, as if there were strings on a guitar. Of course, these are at different frequencies. And you see two beams here, so which can both move. They're coupled to an optical field that is actually confined in the small gap between the beams, and the motion of the beams changes the frequency of the optical field. And so when you then this allows on the one hand to read out the motion of these different mechanical modes very sensitively. Here you see the optical spectrum using a laser that's shining from the top, and that is just reflected from the sample. The laser will be modulated in time at the frequencies of these systems. That's what we detect here. And so these different mechanical modes, they will form the nodes of the networks that we will induce. And the networks we can induce through optical forces themselves, because what happens is that if you take a laser that is slightly detuned from the cavity resonance, now a small displacement of one of these beams will cause a change of the intensity and thereby a change of the force. And so you have a force that acts on these mechanical resonances that is proportional to their displacement. That is like a spring effect, and it is controlled through the optical power. So on a single resonance, you already mechanical resonance, you already see that to tune the laser frequency across the resonance, you can either soften or stiffen the intrinsic frequency of this resonator, but also this creates springs between the modes because they're all coupled to the same field that is squeezed here in this gap. And so one can create interactions between these, where the one thing we still have to remind ourselves of is that the frequencies of these beams are different. And so to overcome that, one can modulate the intensity of the laser in time. And if you do that at the difference frequency of the mechanical modes, you can work out that the effective interaction that you induce is a beam splitter interaction between the mechanical degrees of freedom. So a hopping one mode to the other, if we select our modulation frequency, our optical modulation frequency to be equal to the difference. If you select it to be equal to the sum, for example, 2 times the frequency of a single resonator, then this is exactly, of course, what a child on a swing does, and you induce single mode squeezing. This sum of 2 different modes will induce 2 mode squeezing associated with these squeezing Hamiltonians that I was discussing earlier. Now let's first briefly look at what that looks like in the experiment for the beam splitter interaction. If we take again two mechanical modes and now we read out their motion with one laser and we modulate the intensity of a second laser at the frequency difference, so 1.5 megahertz in this example, we come in at normal incidence here and just detect the resulting thermal eigenmodes, and they are you see that they are split because now we create well, this is just normal mode splitting. We create strong coupling between the two mechanical modes with a rate that's controllable through the intensity of our laser and the depth of our modulation. So that's nice. This is a beam splitter interaction. So importantly, though, since we are converting frequency in the process, we can also again gain control over the phase of this interaction. And since the Hermitian conjugate process has the negative phase, we now play with the relative phases of these couplings. We can induce some interesting behavior, including effective magnetic fields. So for that, we need to create a loop. So we take now 3 resonators, all coupled to a single optical field that we modulate at 3 different frequencies at the same time. And we control the relative phases of these 3 modulations. If you do that, you can induce a total phase of signals traveling around this loop that mimics a magnetic flux. And so this biases the system. It breaks time reversal symmetry for the sound. And you see that because now the spectra, basically this is one of the, that's this one, it's one of the peaks of the spectrum. They split in a triplet now because we couple 3 modes. And you see that the total phase, which is a magnetic flux synthetically, controls the spectra. And it also means that an excitation on one resonator will hop in a chiral fashion along this loop, really signaling the broken time reversal symmetry and the fact that we can control this with this synthetic magnetic field. Now one can use this to basically make an isolator by exciting one resonator and then establishing rates that are equal to the dissipation rates of the resonators. And so what I show here is an experiment where we measure what we call the susceptibility matrix. So that means we drive one resonator, A1, A2, or A3, and we might measure how much is the other resonator on the vertical axis here excited. Okay, and so if this is asymmetric, and this block here of A1 and A2 is clearly asymmetric, of course, this is a pure isolator, if you will, because you have transmission from 2 to 1 in this case, whereas from 1 to 2 it is blocked, and you can control this this direction. This susceptibility matrix is closely related to the scattering matrix of the system. Now, in principle, this was for us the tiniest loop. In principle, you can see the emergence of quantum Hall physics. This is possibly the smallest quantum Hall effect you have seen, because we take just 5 meta atoms, if you will, 5 mechanical resonators that are coupled via equal fluxes. And what you then see is that if you look on the central node, you see a gap between the 2 states. Whereas if you look at the edge, you see that there's extra states that bridge that gap, and these are living at the edge. They're actually flowing in a chiral fashion. We've been able to see that too, and these are like the edge states of a quantum Hall insulator. Of course, how we just look at only the central node or the edge node in this network is that they live at different frequencies. So we can just select the frequency at which we probe the spectrum, and we see a different result. Good. This is oh yeah, sorry. And in principle, you can think of scaling up this these kind of lattices to larger dimensions. Here we use this purely this synthetic dimension, higher overtones of the strings as the different nodes of our network. In principle, you could also think of using a spatial dimension and using different cavities to couple multiple modes together. This is something we haven't done yet. But I want to move to going beyond just these beam splitter and Hermitian couplings and induce the squeezing. And basically, we can do that through 2-mode driving. And in view of time, I will skip 2 slides and tell you that we're going to implement this Kitaev chain by looking at a two-mode squeezing. So we now drive two mechanical resonances at the sum of their respective frequencies, and this induces precisely this pairing term that we want to have adjacent to the hopping term. So if you and then we can implement this effective Kitaev chain. But let's first actually, before we do that, look at only a single unit cell of this chain. So just two modes that we couple simultaneously via these two interactions. And so this is again what we're after. If we look at such a unit cell, then this displays some interesting behavior, which is that if we look at the equations of motion, now separating the equations of motion for the different quadratures, so the x quadrature of the first resonator and the p quadrature for the first resonator and those for the second resonator, we need to do that because remember, when we have squeezing interactions, different quadratures can behave differently. And so how? Well, if you look at for example, the x quadrature of the first resonator, you see that this is coupled to the p quadrature of the second resonator, so it's another phase, via a rate that is proportional to j minus lambda. Whereas in the opposite direction, if you look at how the p quadrature of the second resonator relates to the x quadrature of the first one, you see that there's a different rate. Somebody's trying to draw on my screen, you see. I don't know if this is a comment or accidental. Anyway, sorry, I'm being confused. So now, if you make the rates equal, j and lambda, so the hopping and the squeezing rate equal, then you can see that actually we can totally block the transmission from P2 to X1 and only have it from X1 to P2, where we can acknowledge that also there is a transport that's going in the opposite direction, but it is for the orthogonal quadratures. So this is an interesting system where we have a unidirectional like behavior, but it depends on the phase. And this we can see. Here you see the transmission as a function of the quadrature angle, so as a function of the signal phase. And you see that it is unidirectional, so you have a transmission in one direction and a blockage in the other direction, but it changes the direction if you change the phase of the signal. And so, like before, we had an isolating type behavior, but here it depends on phase. And in fact, you can prove that in this case, time reversal symmetry was not broken. So this mechanism is slightly different. Here we have an interference between these different processes, the beam splitter and the squeezing interaction, where in the case where you break time reversal symmetry and create an isolator that is independent of phase, you really have a magnetic flux, and you can recognize a loop that you cannot recognize here. So if you want to know more, we identify the full class of systems in which this kind of behavior occurs in this preprint. Because there's actually a larger set of systems where this occurs. This includes the Kitaev chain that we then set to implement. And so what does that look like? Well, if we couple now multiple resonators in a chain, like 4 here, and we do the experiment where we measure the susceptibility matrix again, then we see that we create this unidirectional behavior for the orthogonal quadratures, so different phases in opposite directions, and you can really measure that. Here you see that if we launch the X quadrature in resonator 1, it propagates all the way down to 4, but only in that direction. If we launch 4, it doesn't propagate backwards, and it's precisely the opposite behavior for the P quadratures. So you have this clearly, unidirectional behavior. And this is somehow reminiscent of a famous model for a non-Hermitian topological phase, which is the Hatano-Nelson model, where you have unidirectional hopping, meaning that you have hopping that is different in one direction than in the other. This is a slide that I took from our collaborator, Andreas Nunnenkamp. What is special for these kind of systems is that they are clearly non-Hermitian, right? With transport being different in opposite directions. It also means that the spectrum is complex, so the eigenvalues are complex. And if you look at this system and one under periodic boundary conditions, so we take a chain and we close it because of the periodicity. Of course, the spectrum must be equal at both sides of the Brillouin zone. And since that basically means that it traverses a closed path in the eigenvalues traverse a closed path in the complex plane. And so what has been recognized is that there is a strong difference between the eigenvalues if you have a periodic boundary conditions where they exert this or they display this loop in the complex plane, or for open boundary conditions. So there's a strong dependence on whether you link the last side in the chain to the first one or not. And people recognize that you can associate a topological invariant with this in principle when you think about how does the spectrum wind around a point in this plane. What is, however, interesting to note is that if you look at the eigenvectors, then you see that the eigenstates actually of all of the states, all of the bulk states, they actually pile up at the edge of this system, and they do so when this so-called point gap, when this circle behavior in the complex plane exists. And there is somehow a contradiction in that, because even though you could ascribe a topological invariant with the winding associated with this loop, that does not seem to predict the existence of a single state at the edge. So bulk boundary correspondence somehow appears to be broken in this system. So even though there's this interesting behavior of the non-Hermitian skin effect, there's not a single state that is associated with the edge. Now, there's been a lot of work on this. I want to, especially in the theoretical domain of how to think about this. I want to point to a single one from our collaborators, and that describe in these two papers. They mentioned the notion that, look, if you imagine, if you calculate take the winding of this complex spectrum around not any point but the origin specifically in the complex plane, and you look not at the eigenvalues but at the singular vectors of the dynamical matrix, if you will, then you actually see that that specific winding number does predict the existence of a single singular vector that is localized at the edge. And so there is a certain way to see the bulk boundary correspondence, again, to restore it basically. And this singular vector that is now directly linked to a physical phenomenon, which is directional amplification in this chain. So in this case, the non-Hermitian topology calculated through the winding around a zero in the complex plane here, is linked to directional amplification, and it's the topologically protected feature. And this we see actually in our system if we change our the magnitude of both our hopping and our squeezing rates. We can induce a gain in the system owing to the squeezing, and so we see that the signals are amplified along the chain. That's what you see here, and the signal for the orthogonal phase is amplified in the opposite direction. And so you see here behavior that's reminiscent of the Hatano-Nelson model, but basically two copies of it, one for each phase. And this is then a canonical feature of the bosonic Kitaev chain in these systems, including the exponential scaling of the amplification with the size of the system. Now, I was telling you that one can associate this singular value with and the existence of in the Hamiltonian of a specific singular value with the a single channel for topological amplification. And so that's also what you see here, except that we have two singular values, okay, one associated with each. So this is the measured singular values of our susceptibility matrix. And we see that with this, the longer we make the chain, the larger the gain along the chain, or sorry, the larger the gain, I should say, the more this value, which corresponds to the amplified signal, separates from the other singular values that you can associate with the bulk, quote unquote. Okay. Now, yeah, and this amplification, as I mentioned, is exponential. Now, we can also see the sensitivity to the boundary conditions, because if we take the system under open or under periodic boundary conditions, we can simply do that by adding one extra pair of links connecting the first and the last side on the chain. We see that under periodic boundary conditions, as soon as the system enters this topological phase, it becomes unstable, and we see that as a self-oscillating behavior that is absent under open boundary conditions. And so this kind of a strong strong sensitivity to boundary conditions is on one hand related to the Hamiltonian model, and it also shows you the different topological nature as soon as you cross into the regime where you wind the origin. Now, interestingly, in this system, there are some extra degrees of freedom that you can have, because one can play with the phases of the interaction terms. Again, these are just phases that we dial in on the electro-optic modulators that control our laser intensity. And we see that there's actually a stark difference if you choose those phases in this model to be purely imaginary or purely real. The system behaves very differently. In the system, as I showed you so far, it shows this very strong dependence on the boundary conditions and the difference between open and closed boundary conditions. Whereas if you change the phases of these couplings, you see that the behavior is very different. Now, basically, the energy only propagates to the next, or to the nearest neighbor, and not beyond that. And that can be understood by the way that the quadratures are connected now. You can do a gauge transformation and see that the quadratures are linked to their neighbors, but from there the quadratures are forbidden to block or to go out, owing to this phenomenon that we dub quadrature nonreciprocity. So it's an interesting way in which this, the dynamics is controlled in these chains. And also that you can, again, associate with the topological nature or the topological description of this chain. If we call the non-trivial regime that where the system is self-oscillating, we saw that before. Self-oscillating under closed boundary conditions. And here we see that actually this behavior corresponds to one where you do not have directional amplification. It's this point here. Oh, sorry. But there is a point gap in the system, and you see that in the dependence on the strong dependence on the boundary conditions. And this behavior here is the special case where the point gap is closed, and this dependence on the boundary conditions is much less strong. All right, so here we've started to explore, the different kind of dynamical phases that you can have in this special system. There's one more thing that I would like to show on my last slide that is a potential prospect. Besides serving as an interesting type of topological amplifier, these kind of systems have also been proposed by McDonald and Clerk as potentially interesting for sensing, because since there's this unidirectional propagation of an amplification of signals in one direction, a signal can propagate in one direction for specific phase, but not backwards, unless a resonator is perturbed and slightly changes its frequency. Then that's kind of a detuning, mixes the quadratures, it transfers one quadrature to the other, and that may then exhibit a strong amplification in the backwards direction. So if you monitor the orthogonal quadrature of the first resonator versus what you send in, you will see a strongly amplified signal when there's a signal present, or a detuning that one might want to sense in the last resonator. And this is larger. The longer you make the chain, the more gain you build up in the resonators, and there's this characteristic scaling of this responsivity with the number of resonators. That is exponential, and that is as predicted by the theory, and that may very well be an interesting way to build a non-Hermitian sensor by exploiting this kind of unidirectional behavior. There's a lot more to say and to investigate about this. Does it really enhance the signal-to-noise ratio, for example, for all kinds of different sources of noise? I think there's a lot more work to do. But with that, I have come to the end, and I hope that I showed you how this kind of platform in which we have parametric control over many multiple mechanical modes through laser or modulated laser fields and radiation pressure forces is very versatile. It can basically implement any quadratic bosonic Hamiltonian of our choice. I've shown you some examples, looked at this phenomenon of quadrature non-reciprocity, and then specifically the special properties associated with this bosonic Kitaev chain. And with that, I want to thank the people that were involved that I named already at the start, and you for your attention.
Thank you very much, Ewold, for this very nice and interesting talk. Are there any questions? We have one. I will unmute you. Okay.
Yeah, okay. Can you hear me?
Yes.
Yeah.
So thank you for a nice talk. My name is Grigori. I have a question, the following one. So J and lambda, are you able to change them for any pair of nearby bosonic modes, or only for the whole lattice?
No, we can. Great question. We can in principle change them for any pair of modes. The funny thing is that in our spectrum, sorry, I wanted to show it. I can probably reach it. In our spectrum, it's not harmonic. This is actually standard for nanomechanical string resonators. So as you see, the frequency spacings between these modes, they're not equal. And that means that we apply a modulation tone on each pair of modes individually, and it only addresses that interaction. And the same holds for the sum frequency tones. So you can imagine that for a long chain, we actually have a lot of different modulations that are going through the system at the same time. But like that, we can, through the different amplitudes and phases of those modulations, implement any or address any individual coupling rates. Yeah. And
how fast can you change J and lambda if you want to change the configuration?
I would say as fast as our electro-optic modulator allows doing this, which is a 10 gigahertz. Okay, so way faster than the dynamics of the mechanical modes that we are interested in, which is in the megahertz regime, and our lifetimes, as you can see from the narrow widths of this system, are even much smaller. So in principle, practically instantaneously. Yeah.
Okay, this is very interesting. Yeah. Okay, thank you.
Yeah, you're welcome.
Great. Further question, or maybe I can follow up on this. Could you also use this control that you have to, for example, study the role of disorder in these systems? And have you thought about this?
Yeah. So basically, the last experiment that I showed was already kind of a way to induce some special disorder. Because, okay, what we do in this experiment is that we establish the chain, and we perfectly choose our sum and their difference frequencies to be fully resonant along the whole chain. And then we intentionally induce a detuning, not by actually changing one of the resonators, but by changing the frequency at which we couple the resonators. So just slightly detune away from the exact difference in some frequencies. If you do that, it's mathematically equivalent to actually having a shift of the frequency of the last resonator. And like this, you can imagine that we can do this on any of the links. And yeah, as I said, create an arbitrary Hamiltonian, including any type of disorder that one would like to simulate. In fact, we could, in principle, very rapidly vary the disorder at will.
Very interesting. So you said that you don't drive exactly at the sum and differences for this last one. Is that, did I understand?
That is right. So we basically, we imagine that this resonator would be at a slightly different frequency. We calculate the sum and the difference frequencies. If it were there, since its actual frequency is slightly different, well, this is the detuning that you then synthesize, I would say.
I see. And it still has a time-independent description in the correct frame.
Yes, I think this is. I think you're correct. Yeah.
Okay. Okay. Are there any other questions?
I have a brief one. So, in your system, what limits which size of system you can have? Like,
yeah.
What's like the best you can do? So, how many harmonic oscillators you can get that?
Here I showed you 5, right? And also in the quantum it was 5. So apparently that was what we could do so far. Now we have some ideas and some ambitions to scale this up. I already showed you one idea to use a spatial dimension.
Mm-hmm.
In principle, you could also scale up further in the frequency dimension. Of course, there's many harmonic modes. Mm-hmm. They become less and less strongly coupled to the optical field. So it becomes harder and harder. But there's actually a simple way in which we can address them as well, and that is to actually cool down our system. This is a little bit counterintuitive, but if you cool down the system, you make all of the dissipation of the mechanical dissipation becomes much smaller. That means that the rates that you want to, the coupling rates that you want to induce also become smaller, because basically what you want to have is coupling rates that are equal or larger than the dissipation of the system. And you can open interesting band gaps and things like this. Okay? Mm-hmm. So if you make the dissipation smaller, you can work with smaller intensities, and that's one way to address this. I do want to say one other thing though. The complexity in our current implementation does go up, because as I mentioned, we need separate control for all of the, basically we have one drive, one modulation that we send to one modulation at megahertz frequency that is responsible for each rate in your Hamiltonian. Okay, so 5 resonators coupled via 2, this is already 10 RF tones that we send. And then what I did not tell you is that there's some extra tones that we use in order to equilibrate also the damping rates of these resonators actively, which makes the system even more pure. And so the kind of control that you need becomes rather complex in the time domain. It may be that therefore this extending also in space is a nice way. Mm-hmm. I would argue though that a lot of the interesting dynamics you can already see in relatively small systems. So that's where what we're exploring for the moment.
Oh yeah, definitely. Definitely. Okay. And all the experiments that you showed, they were like made at a cryo temperature, or it was?
No, this is thank you. And this is all at room temperature. Mm-hmm. So I mean the motion that you saw was at the level of the thermal fluctuations. This is picometer level motion. Mm-hmm. One can imagine doing this also for in the quantum domain, meaning that if you cool these mechanical resonators down such that they only have that they're in their ground state, you could in principle imagine, seeing the very same physics, but then for quantum fluctuations rather than for thermal or coherent excitations. the physics wouldn't change so much, but maybe there's some applications there that might be interesting. Yeah.
Mhm. Yeah, because I was wondering if, if you put like this thing like in a cryo, and then you can use like this non-reciprocity combined with non-Hermitianity to kind of generate like this weird collective quantum states maybe of mechanics by just, tuning the light accordingly.
Yeah, I think so. Yes, I think the answer is yes. There's one comment to make, which is that everything that we do here, both the beam splitter and the squeezing interactions, they don't involve nonlinearity, so it doesn't create states with like negative Wigner functions or so. It does, but you would create entanglement in these chains and interesting kind of squeezing distributions, perhaps that might find an application. One of the most obvious being, by the way, quantum amplification of signals. And another comment that I could maybe make, just to admit that life is not super easy, is that the drives that you use here, since they are photonic in themselves, they would induce some shot noise fluctuations on the resonators, radiation pressure shot noise, that would add to the fluctuations, and that it would still be quantum noise. It's actually interesting, but it might forbid you from doing this in the ground state unless the quality factor of the cavity is small enough so that you mitigate this. Sorry, high enough, I should say. The quality factor high enough.
Yeah, thanks.
Thank you. I don't see any more questions. Thank you very much for this great talk, Ewold. Next week, we have a talk by Professor José Lado, so join us for us. We're looking forward to see you then. Thank you very much for joining us today.
Thank you.